In this video, we're going to look at what happens when you add in something into this sort of setup, heat sort of setup, if we have a state change. And the state change mathematically is going to be governed by this Q is equal to mL, part of the formula. So L here is what's called the specific latent heat. And what it is, well, first of all, there's two types of it. So there's specific latent heat of fusion. So this is when you're going from solid to liquid, so basically melting, or going from liquid to solid, so if you're freezing. L here is the specific latent heat of fusion. And when you're going, the other state change, if you're going from liquid to gas, or gas to liquid, you've got the specific latent heat of vaporization. So what these mean, what this means is, when you have a change in state, you don't have any change in temperature. If you have ice, for instance, as an example, ice is at 0 degrees Celsius, it's solid ice at 0 degrees Celsius. But as it melts into water at 0 degrees Celsius. And that takes heat energy, but it doesn't change the temperature. So that's called latent heat. And for each substance, the amount of heat energy that's needed, say for 1 kilogram of that substance, to just change state is different. It's a little bit like specific heat capacity, but for state changes. So there's a different amount of energy needed to change state for 1 kilogram of each substance. So as an example, for water, the specific heat capacity, or specific latent heat of fusion of ice, is 3.3 by 10 to the 5 joules per kilogram. Now, it isn't joules per kilogram per Kelvin, because there is no change in temperature here. It's just a change of state. So if we had a kilogram of ice and we wanted to melt that into just a kilogram of ice at 0 degrees, and we want to melt that into a kilogram of liquid water at 0 degrees, it would take 3.3 by 10 to the 5 joules to do that. So a lot of energy. So we're going to do an example using this part here, and it's in addition to what we've been doing previously, which is just mixing things of different temperatures. And so we're going to start with the setup where we have 200 mils of water at 0 degrees Celsius, 20 degrees Celsius, sorry. And into that, we're going to add an ice cube. So this is 10 grams of ice. And for now, we're going to say at 0 degrees Celsius, because we're going to come back to that later. In later examples, it won't be 0 degrees, it'll be lower. And this is the before case. Before. Now, after we do that, what we're going to end up with is 200 mils of water here. And kind of added into that will be an extra 10 grams of water from the melted ice. So we're going to have our water here and our ice kind of mixed in along with this, the ice water, the melted water from the ice cube, mixed in with this. And this will be at a temperature lower than 20 degrees Celsius. Like in real life, we add ice cubes to cool things down, cool drinks and so on. So it'll be lower than 20 degrees Celsius. So we have to figure out what that temperature is, and we're going to call it X, like we did previously. Okay, how do we start this? Well, we start, this is our after case, actually. Okay, so how do we start this? Well, we start the same as we did before. So what's the hottest thing in this setup? Well, it's the water here. Oh, we're going to assume that the container as well doesn't take or give any heat energy. It's just an insulator, we'll say perfect insulator. So we only care about the ice cube and the water that's in here for now. So in this example, we're going to take it that the water is the hottest thing in the setup. It's 20 degrees Celsius. So it's going to give its heat energy to the ice cube. And the ice cube is going to gain heat energy. So the heat energy lost by the water is going to be equal to the heat energy gained by the ice cube. First to change state, so that's why I'm putting a little star here. And then after change of state, you're going to have 10 grams of liquid water that's going to be mixed in with the other 200 mils of water that are there. And that's going to increase in temperature from 0 degrees up to some final value, like our previous examples. So that's going to be Q. We could call this ice as well, even though it's ice water. We call it Q ice water, right? So this is the increasing in temperature. If this was 10 grams of water at 0 degrees mixed with 200 mils of water at 20 degrees Celsius, we'd be back to our previous examples where we have the heat energy given off by the water that's in here is equal to the heat energy gained by the 10 grams of liquid water at 0 degrees Celsius when they're mixed, and we could work out our temperature. But we have a state change in here, so we have to handle it this way. All right, what do we substitute in for QW? Well, it's MC delta theta like before. We'll fill in the subscripts in a minute. This is a state change, so we have to do that as ML. We put in subscripts on that too. And this is the Q. This is a normal Q. Again, this is MC delta theta. This is for the liquid water that's left after the ice cube melts. Okay. So what are my subscripts here? Well, this is the mass of the water here. This is just the mass of the water in the beaker. The specific heat capacity of water. And delta theta 1. And delta theta 1, keep in mind the water is going to start at 20 degrees and finish at some temperature lower than 20 degrees. So for that, we're going to put in 20 minus x, whatever x is here as our final value. M here is the mass of the ice. Now the mass of the ice is 10 grams. So we can put Mi for that. And L here is the specific heat, or the specific latent heat of fusion of ice or water. So that is, we can put Li there for that, which is Lw here, same thing. M here, now when the ice cube melts, you have 10 grams of ice, and when that melts, we'll end up with 10 grams of water. But that water has the same mass as the ice cube. So I'm just going to put Mi for that. It's going to be liquid water, so it's going to have the specific heat capacity of water. And the change in temperature is going to be delta theta 2. The reason that it's delta theta 2 is because we're going to have a final temperature overall here. This water is going to start at 0 degrees Celsius, and then it's going to increase in temperature to some value x. So my overall change in temperature here is going to be x minus 0, or just x on its own. Right, let's sub in some values here now. Mass of the water, well, we've got 200 mils of water, so that's 200 grams. So in kilograms, that's 0.2. Specific heat capacity of water is 4180. And my change in temperature, we said, was 20 minus x here, is equal to. The mass of the ice is 10 grams, but in kilograms, that is 0.01. And the specific latent heat of fusion of ice is this value up here. It's 3.3 by 10 to the 5. We won't put in any units. Plus, now for this term here, the mass of the ice is still the same, 0.01, same as this. Specific heat capacity of water, 4180. And then we're filling in x minus 0. I'll put it in as x minus 0 for now. Right. Let's do a little bit of the calculation here. So what's 0.2 by 4180? 4180 is 836. So it's 836, but we're still multiplying that onto 20 minus x, like that in a bracket. Now this is 0.01, that's a hundredth, so that's 10 to the minus 2. And that's multiplied by 3.3 by 10 to the minus 5, so 10 to the minus 2 by that. I can just change my powers here, I can reduce it by 2. 3.3 by 10 to the 3, like that. Plus, and over here I've got 0.01, so that's a hundredth again, so that's easy by 4180. We can just move the decimal place twice, and we'll end up with 41.8. But we still have this bracket with x minus 0, but x minus 0 is just x. Okay, 836 by 20 is going to give me 16,720, right? So I've got to do this bit first, and then I've got to multiply 836 by minus x, so it's a plus by a minus, so it's minus 836x. Now, this doesn't change. The only thing is that this is 3.3 by 1,000, so that's 3,300. So that's easy. Plus, and over here I have 41.8x. Easy. Now, I've got to gather up all of my x terms on one side and all my constant values on the other. So let's gather up all my x terms on this side. 41.8x, because it's positive here. Well, on this side, I've got minus 836x. So to get rid of it on this side, I'd have to add on 836x. So I have to add on 836 on this side, plus 836x, like that. On this side, I've got 16,720, And I've got 3,300 here, and this is positive. So in order to get rid of it from this side, I'd have to subtract 3,300. So I have to do that on this side as well. Minus 3,300, like that. Okay. What's 41.8x plus 836x? That's going to be 877.8x on that side. On this side, I've got 16,720 minus 3,300, which gives me 13,420. I'm going to switch these over to the other side, just so that it makes it a little bit easier. So 877.8x is equal to 13,420, like that. Now this is 877.8 multiplied by x, so I want to get rid of the 877.8, so I would want to divide this term by 877.8. And if I do that, I have to do it on this side as well, so I end up with x is equal to 13,420 divided by 877.8, like that. And I get x equals 15.29 degrees Celsius, which makes loads of sense. It makes sort of sense if I have 200 mils of water and I add in a kind of a fairly large ice cube, I'd end up with just over 15 degrees of water. You know, the water would be about 15 degrees. The answer makes sense.